Okay, hello everyone. So I am Xavier Rival. I'm going to chair this first session on program analysis. So welcome to the dortoir room, which is where I guess people used to sleep. So, but we are not going to sleep today. We are going to start with program analysis talks. So, and first, the first talk will be given by Gregory Blike on a modular static cost analysis for GPU warp level parallelism. So please.
Good morning. Thank you for coming to a modular static cost analysis for GPU warp level parallelism. My name is Gregory Blike. This is work done with Hannah Zicarelli, Udaya Sathiyamoorthy, Julien Lange, and Tiago Cogumbreiro. Work done at UMass Boston in collaboration with the Royal Holloway University of London. Today we're going to be talking about why GPUs matter and the challenges of analyzing performance bottlenecks. We'll go over what it takes to analyze GPU kernel performance, give some theory, the relational cost analysis of GPU kernel analysis, and then go into our implementation, Pico, which is a tool to analyze GPU kernels. So why do GPUs matter? And what are the challenges in analyzing those performance bottlenecks? Performance is the raison d'etre of GPU programming. Consequently, GPUs are everywhere. The LLM revolution is powered by GPUs, where GPT-5 was trained using 200,000 GPUs. Scientific advancement is powered by GPUs, where 9 out of 10 of the top supercomputers are powered by GPUs. And so we want to be very careful with GPU programming, since it's such a desirable property for performance. Developers for GPU programs really want to manage those resources well. They want to maximize parallelism, where more work done concurrently means less time consumed, optimize memory access, because there's only so much memory bandwidth to go around, and to do that, they need to understand the computational model of GPUs, which is single instruction, multiple thread, and manage the control flow for those threads. And because we're so interested in their performance, that these programs are intended to run fast, we want to understand how they work. And there are several approaches for doing this. NVIDIA has a profiler, nSight, which is a dynamic analysis. It provides no worst case analysis, just counts the number of problems that occur, and provides some symbolic execution tools as well, which detect only the presence, but not the frequency or cost of some of these bottlenecks. And there are also static approaches. Pug and GPU Drano detect the location of these performance bottlenecks, but not how frequent. And the state-of-the-art RaCUDA has limited support for GPU-specific semantics, which lead to over-approximations, and cannot reason about the precision of the analysis. That is, there's no exact costs. So the problem of cost analysis for GPU kernels is very important to us. We want to understand the cost of that performance bottleneck. And in doing so, we want to account for how many resources are needed to run the program. And we want to motivate counting active threads per memory access as one of those approaches. In this summary slide, we have a CUDA program, and we're very interested in how many read accesses happen here highlighted. And over the next few slides, we're going to talk about how we get to this solution where the cost is W squared plus W over 2. Where W is the number of concurrent threads. So why is that cost, W squared plus W over 2? And to do that, we need to understand warp semantics. So for that CUDA kernel that we have one particular interesting variable at the top, that thread-idx.x, which is a unique thread identifier provided to every thread in a warp, which is a collection of threads that are executing in kernel lockstep. That is, every instruction in the thread happens at the same time. And then some of those threads may be enabled or disabled, depending on the control flow of the program. So in an example where we have 4 concurrent threads, we have this view of that same for loop, where each of that thread-idx.x, which I might call the thread ID, is replaced with its unique identifier, and we have those 4 loops. Now let's kind of understand how it executes. In the beginning, we have all of our threads running. There are 4 threads that access this array for reading. We increment x as usual for a for loop, and one of our threads terminates because its test condition no longer passes. And likewise, and then as we move along, only 3 threads are active. Increment again, another thread disables, and this continues with each thread disabling as it progresses until no threads are active and the loop terminates. So counting that active threads per memory access gives us this nice triangular shape, which allows us to give a series summation for the number of active threads and the number of read accesses in the loop. And so thread divergence, which is this property of each of the threads being enabled or disabled separately from the rest, is an important core aspect of 2 major performance bottlenecks, bank conflicts and uncoalesced accesses, both of which are memory performance issues where threads are competing for memory bandwidth. And the key takeaway for all of this is that precisely characterizing that thread divergence is precisely characterizing the performance bottlenecks. That takes us to our cost analysis, which is our contribution. We translate the concurrent warp semantics into a sequential program and then build on the vast literature of cost analysis of sequential programs. We do that in these steps. The CUDA kernel, there on the left in A, is translated into our intermediate representation, memory access protocol, where we remove a lot of the details of the execution of the program and focus just on the memory access. We then translate that concurrent program into a sequential cost program with our analysis, and then use regular sequential cost solvers to reduce this into an expression. And the major contribution here is to prove the correctness of step 2, that translation between our intermediate representation and a sequential cost program. And that looks a little like this. The sequential program captures the control flow of the warp and offers us this tick expression, which shows how many resources are consumed each time this part of the program is executed. And off-the-shelf tools can help reduce this into our symbolic expression. And so if we replace this with our four threads in our warp, as we did before, we can see that we have the number of active threads is the same as the cost from this enumeration. And so as we progress, one thread terminates and our cost reduces. And again, this sequential program was produced by our analysis. And as we progress, we continue to see that these maintain the same value until the thread terminates, or the loop terminates. So how can we guarantee that sequential program captures the cost of warp semantics? And that's the theoretical framework that we built to relate the cost of the concurrent and the sequential programs. And that is to show that the two programs have the same cost. Here, for our expression, we have gamma as our usual typing environment. Phi is a vector of Boolean expressions, which represents the active threads. P is our concurrent warp protocol. Tilde our parametric cost relation, and S is the sequential cost program. And that cost relation, equality greater than, less than, allows us to bound the relationship between the two costs. So let's go through an example. Here we have our closed environment, and we start with all of our threads being true or active. We have that protocol here on the left. In this case, this is partially through our analysis, so that access to array A is not a typical like C++ array access. It's a vector of costs that come after our analysis. We have the sequential cost here on the right with the analysis of the tick with W minus X being the cost and equality between them. So what does it take to prove that those loops have the same cost? We need to prove that the iteration spaces have the same number of iterations. And in this case, we also, we see that it is of type D divergent, that the threads are not all the same at the same time, which would be a uniform thread. We also need to prove that the bodies have the same cost. In this case, we have a subscript for that divergence for the ranges where X holds this divergent property, and the cost relation between them. And we can see here on the right what we saw earlier from the example of the costs between the scalar and vector costs. And here's where that array access is a series of numbers. So that thread divergence is captured in the type annotation for X. We see that we have exact costs and the symbolic costs per iteration. And our theory is driven by two core ideas: that loop analysis, which allows us to relate the iteration spaces, and a metric analysis, which allows us to relate the symbolic cost, which is a parameter of our theory and why this is a modular static cost analysis. More generally, the capital I is the loop analysis to do that relationship for the two ranges, so that if they are the exact same ranges, we can use the same, or if they are bounded above or below, we can use those instead. We compare the loop body while recording the original ranges of X, and we track the uniformity and divergence of the threads in the type system. And so our main result here, so given a metric and a cost relation, if we can derive the cost statically for a protocol P and a program S, then that cost holds dynamically. And the key contributions from this are that the warp semantics are we support warp semantics with thread divergence, which was not previously supported. We can also add the lower and exact bounds, which before we were only able to handle upper bounds, and it's all handled in the same formalism. And we also offer symbolic costs per iteration, where there were only fixed costs before. And all of this has been proven sound with mechanical proofs in Rocq. And so we didn't want to just build out to this theory. We also wanted to test this, since this is used for performance and practical needs. And so we built out a tool, Pico, which follows a very similar pipeline to what we described earlier, where we analyze a CUDA program, extract it into our protocol, our intermediary representation, and perform some analysis, which optimizes our intermediary representation, does the loop and metric analysis, both for uncoalesced accesses and bank conflicts, which proves out that that we are able to use this type theory. And then we support a variety of sequential cost analyzers to do the final analysis, using mostly Maxima as a computer algebraic system. So how does Pico compare to the state-of-the-art RaCUDA? We would like to know how it compares, and so we reproduce the same evaluation that was used by RaCUDA in their POPL'21 paper. And then how often does control flow affect the accuracy of Pico? And so we used a large suite of well-known kernels to evaluate our tool. So in comparing with the state-of-the-art, we are able to add the thread-divergent loops, the arbitrary loop steps, bitwise operators, C++ features. And in the 25 programs that were part of that initial evaluation, Pico was able to give tighter bounds in all cases, or 15 prior with CUDA. 10 of those kernels had problems of some type, and we were able to address those. And in 4 cases, we were able to document unsound bounds in RaCUDA where we did not have the same. And how frequently does this affect the control flow? In that large data set that we had mentioned, we wanted to just show that this is practical, since it is going to be helping developers in the end. So of those 226 kernels, the vast majority of the conditionals and loops, at 75% of conditionals and 85% of loops could be precisely characterized. So we were able to say precisely the bounds that each of those loops would have at runtime, which is, I'd say, pretty good. And I am talking very fast. So in conclusion, we developed a relational cost analysis for warp-level parallelism, and with that support for thread divergence, which is that major contribution. We have correctness for exact over and under approximations. We mechanized all these proof results in Rocq, and Pico achieves the lowest bound in all of those evaluated kernels, 1.7 times better on average. In the future, we want to trade off performance, analyze performance and precision in our metrics. That, of course, we can analyze further to try to bump up that level, but that will come as a trade-off for computation. And we want to be able to report this feedback usefully to developers so that they can inspect their own programs and understand how to make changes. And now that we have a formalism, we can use this for potential program repair to say that if there is a better arrangement of some part of the program, we can report that to the user and offer it to them. So thank you for your attention, and do you have any questions?
Okay, thanks a lot, Gregory. So we have time for questions. So I see there is one over there, so we'll start.
Hi, thanks for the talk. You focused on the correctness of the step 2 in your pipeline, and I wonder about step 1. Mm-hmm. Yeah, how sure are you it is correct?
That the relationship between CUDA and the intermediary representation?
Right.
That was done earlier in our lab. We have another paper on that, on the parsing of the program into the intermediary representation, and I believe we've also formalized that as well.
Okay, thank you. So maybe I will just inject a question that is very related to this one. In this first phase for transition, do you also have the possibility of losing precision, that is, of getting a program after translation that would not let you infer as precise a property as the initial one, or is it exact with respect to the properties that you try to infer later?
I'm sorry, could you repeat the second half?
So when you mix program transformation and static analysis, sometimes you have to be careful whether the transformation done before the analysis may make the job of the analysis harder, because maybe the properties of the translated program are less strong as the initial one. Is it okay? Yeah.
So the intermediary representation focuses just on the memory. Let's see, where do I have this one? Just on the memory access. So the control flow, the intermediary representation basically just manages all of the control flow. And so the analysis that goes into proving that that is the correct control flow this was we get rid of all the information that's not necessary for it. And as we progress from the concurrent to the sequential cost program, I'm just not putting the words. Julien, would you be able to say that?
So if I can, I will go to this step.
Yeah.
So the first step, the translation, in fairness to Greg, is a previous paper we studied in detail. So what we lose when we go to memory access protocols. And there are some conditions, some programs where we will lose some correctness, but this is quite well identified, and we can actually precisely explain where we lose this. So this was not the focus on this paper, so this is not, this is why we don't show this that much here.
Thank you. So.
Thank you very much for the lovely talk. So you mentioned in your future work that you're considering giving some bounds on average costs. this would be averaging over what? Over
this is mostly for reporting, so we're not really sure how to present it to the end user. We have exact costs right now, and we would like to be able to present it so that it's very useful. We're not sure what the users would appreciate the most.
Because right now the problem is that the exact costs might be data dependent and so hard to read, or?
It could be a bit complicated to read, or where to break it down, what to recommend at which stage of the process.
Thank you.
Okay.
Perhaps a tangential question. Could Pico be used, for example, as an oracle to run optimizer, optimize the code?
That's somewhat what we're thinking for the relational cost, for the repair part, is as an oracle, yes.
Okay, so before I move to the next question, maybe the next speaker can start to move on to start to get ready. Thanks.
Thanks for the nice talk. It wasn't clear to me what fragment of CUDA you're handling. Is it, what kind of synchronization primitives are you supporting? Are you supporting tensor cores?
So a lot of the features are a little bit dated in CUDA, but most of the for a lot of the for the CUDA kernels that are available out there, we pulled down a lot of open source programs to verify that what we are able to analyze is actually what's used in practice. We do handle quite a bit of them, but we do not account for all of the newest features from CUDA.
So you do support barrier synchronization and warp level synchronization and so on?
Well, synchronization for these metrics wasn't necessary because we're only interested in reading and writing, but not necessarily that it is managed without like data races.
Okay.
Thank you. I was curious to what extent you think this pipeline could be applied to, say, web GPU kernels or other kinds of GPU architectures, how specific it is?
At the moment, this handles just NVIDIA CUDA. We are investigating what you just said in the browser and like yes. Web GPU. Right. Yeah. But we haven't finished that research yet.
Okay, thank you.
Mm-hmm.
Okay, any more questions?
Thank you for the talk.
Mm-hmm.
You mentioned at some point that you found unsoundness is in RaCUDA. I didn't get from what you said. You said like we did not find as good bounds or something. Can you elaborate a little bit on how did you verify that those were like unsoundness is in RaCUDA and not imprecisions in your tool or something like that?
One, we went and looked at them and analyzed them by hand, and then we went by, and using our formalism, we went through those kernels in Rocq and proved them out.
Okay, thank you. Any more questions? Okay. So maybe we can take a last question while the speaker is setting up, the next speaker. So is there any other question?
I was wondering, often the way you write a program and small details may make it analyzable or more precisely analyzable, if you see what I mean. Did you notice like small changes in these kernels that you analyze, in which one case you get a precise result and in another case you get a worse result? And can you maybe explain the kind of things that people need to avoid if they want a precise result?
Well, thread divergence is the source of approximation. Otherwise, this would be, if all the threads were uniform, they would be sequential, essentially. And so if they're hoping to minimize approximation, they have to find a way of keeping it uniform, and that's, of course, the challenge. And that's why we have our tool.
Okay, thanks a lot again, Gregory, for the presentation.
Right.